Hello, everyone. My name is Logan Arkema, and I have the honor of presenting Residue-Free Computing, an architecture and implementation for users to use their own computer without leaving behind the unwanted and pervasive digital breadcrumbs left behind by many modern user applications. For some housekeeping items, this is the version of the presentation that does not have subtitles except for this slide. A version with subtitles is available at the website on the slide. And also, this paper and presentation represents work I primarily did while at Georgetown University and does not necessarily represent the thoughts, positions, or opinions of my current employer. With that, let's jump in.
As most of us are aware, current privacy work is overwhelmingly what we might call server-side, in that we're focused on what organizations do with our data after they have access to it. Privacy regulations and current research focuses on mitigating the risks of an organization processing, using, collecting, storing, or transmitting or distributing users' data. It's not bad that the focus is here, because these privacy risks scale quickly and are an accurate threat model for most users most of the time. However, it does leave open concerns about the data that isn't sent to other organizations and sits on users' machines. And personal computers store a lot of hidden details, what we call residue, that can provide a strikingly accurate trail of a user's activities on their own computer without their knowledge or consent. Developers lack incentives not to cache data on your computer, privacy policies typically don't address what gets left on your machine, and applications get computational benefits from caching. But this means a lot of potentially sensitive information gets left behind, and very few apps bother to tell their users about it. The appendix of our paper details the residue we found on 20 different user applications in Ubuntu, but residue might include evidence an app was installed, that a privacy-centric app was used, even if its data isn't stored, detailed chat logs and timestamps from apps like Skype and Slack, and without private or incognito mode, browsers will cache websites visited, and the file system itself, as well as many content readers, will store when documents were opened. Therefore, we introduce residue-free computing to allow users to use their machine on the fly without leaving residue behind. For example, let's look at an application, VLC, that stores data a user may consider sensitive without informing the user or providing a clear way to delete the data. In our example, the user wants to watch a query-oriented video, but lives with invasive co-inhabitants that monitor the user's computer use, and the user does not want their co-inhabitants to know they watched the video. So the user, wanting to be private, uses Firefox in private mode to search for a queer poetry event, and they download the file, and then they download it, play it, and remove it from their machine. Later, the invasive cohabitant is able to get their hands on the user's computer and identify files that were modified while the user used the computer. We actually created this list using Residue Free's forensic mode, which we'll touch on later, but nonetheless, they can see a bunch of Firefox files were modified, and more concerningly, some VLC files were modified in what appears to be a hidden configuration directory. And when we grep for LGBT, we see that this hidden VLC file appears to be storing the names of recent videos that were played using VLC without the user's knowledge or consent. And we see that when we open up the file, that indeed recent files are being stored by this configuration file. While there are previous solutions to protect data that is left on a user's disk, these are either inadequate in that they leave recoverable data, or they have high usability barriers, or they do not allow the user to use their own operating system and their own applications that they have pre-installed, or they leave some traces that could be considered sensitive or undesirable. We go into details for each of these previous solutions and their challenges in the paper. So to recap, here are our goals of what we're trying to provide users and the scenario that we are trying to protect them from. To start, an advanced adversary may be able to obtain a forensic image of the file system or just be generally familiar with the state of the user's machine prior to them using residue free. However, they do not install malware, spyware, or persistent access to the user's system. They also don't have network access to the user's traffic. The user then runs their normal operating system and on the fly decides to use residue free. When they use residue free, they should have access to all of their normal applications, and using residue free should feel as identical as possible to their standard use of their operating system, except that the data from their residue free session will not be saved to disk. When they're done using residue free, they exit, and then the attacker is able to gain access to the machine again or for the first time. And even with complete access to the user's file system, they should not be able to identify the apps that were used or the files that were modified while the user used residue free, even if are able to compare a before and after forensic image of the file system. Which brings us to the high-level architecture for residue-free computing. We begin with the user system, for our purposes mainly composed of the user's file system, hardware resources, and system processes, some of which may need to be modified to ensure they don't write sensitive information about residue-free to disk, and the residue-free environment we want the user's applications to run in. The key component of residue-free computing is a volatile virtual disk in RAM. To prevent file carving or later recovery of sensitive residue, it is key that all file modifications occur in RAM and never touch the user's physical disk. To mediate access between the user's permanent file system and the RAM disk, we add a union file system, a logical file system that applications have direct access to, but that just directs file operations to the appropriate disk. Residue-free applications must be able to read and write to the RAM file system, but only read from the user's file system. The union file system should also be copy on write, so that any files modified inside residue-free are copied to the RAM disk, where they can again be read and rewritten without additional calls to the user's file system. Then, of course, we need to set up an execution environment where the applications run, and all file calls made inside that environment must go to the union file system. The final and most challenging component is providing the execution environment sufficient access to the user system resources, such as drivers, input or output, keyring, the user's system configurations, and interprocess communication, while minimizing the risk that these resources store information about what occurs inside residue-free. While doing this, we want to keep residue-free as lightweight as possible. An implementation could conceivably reinitialize many of these services inside residue-free, but that may cause interoperability problems. Slow residue-free down, or in very technical terms, make the operating system cranky. After residue-free exits, the implementation needs to ensure that all residue in RAM is made inaccessible as quickly as possible. While architectures and diagrams are fantastic, here are the details for how we got residue-free to work. We built our implementation in Ubuntu, starting with the basic ext4 file system, remounted with the no access time option to prevent the file system from checking file reads from inside residue-free. We created our RAM disk using TempFS, a temporary file system that lives entirely in RAM, and ensured its volatility and efficient destructibility by mounting eCryptFS, a basic encrypted file system, on top of it so that all contents of TempFS would be encrypted as they are written to RAM. We then used UnionFS to implement the Union file system over the ext4 and TempFS disks. As some astute observers may have guessed by the color change, we used a Docker container for our execution environment. This made it pretty easy to ensure that all file calls were made to the UnionFS file system. Mediating access between residue-free and system resources, namely service daemons, was again challenging and where the bulk of our time was spent. For example, we provided residue-free access to the user's network namespace so it could easily connect to virtual Unix sockets, as well as direct access to other Unix sockets like dbus and X11 for essential interprocess communication with resources that the certain user apps required. Since we provided means for residue-free to communicate with the user system, we had to modify certain system processes to ensure they didn't save any sensitive information or residue that they may have received from residue-free. For example, we temporarily disabled syslog and journald, modified application use tracking kept by GNOME, and restarted pulse audio inside residue-free. For cleanup, we simply destroyed the eCryptFS encryption key to make the residue inaccessible and unrecoverable, and then restored system processes we modified back to their original state, including restoring access times to the ext4 file system. In addition to the privacy-centric architectural requirements we established for ourselves, we wanted our implementation to be as usable and useful as possible, both for end users and the research community. To that end, we included an option during installation and a small side script that adds a run-in residue-free option to any desktop application icon in Ubuntu. With this, a user can launch residue-free with a click of a button and entering their password. We also created a designated folder that will save only files placed in that folder back to the user's permanent hard disk. For instance, if a user wants to save a file without storing residue about what application they used to download that file, they could use this designated folder inside residue-free. For researchers, we also added a forensic mode, which functions just like the residue-free we just described, except instead of storing then destroying all file modifications in a volatile RAM disk, they're just saved in a designated location on the user's file system, which makes it trivial, especially when combined with diff, to isolate the specific file changes caused by an application. Alright, here's a demonstration of how residue-free works and the features it can provide. We're going to be performing pretty much the same actions that we did earlier, but this time using residue-free mode instead of Firefox's private mode. So you can launch residue-free with the click of a button and entering a password. And we get a notice saying that all files have to be saved to this special directory to be saved, and we'll cut to downloading the file. So the user is going to download the file, but they saw the warning that popped up when they initiated residue-free saying that if they don't save it in this keep files directory, then it is going to be erased. And while this isn't a typical user behavior, we want to demonstrate the ability to save persistent files. So they're going to save just the film itself in the keep files folder, and that's going to be saved. Alright, so the file's been downloaded and the user is going to exit out of Firefox and residue-free. They can notice that residue-free is exiting, and now they want to watch the video, so they're going to use residue-free again to launch VLC. Continue. Go to where the file was saved on their desktop.
From the Library of Congress in Washington, D.C.
Then they're going to exit their VLC and the residue-free section. Now, this was all in residue-free's private mode, not forensic mode. So in forensic mode, when we did those exact same actions, even using Firefox in private mode, we got all of this data. And now, if we go back to the user's home directory and just try to find all the files that were modified in the last 5 minutes, nothing. None of that incriminating data, none of the VLC files that were modified, or any of the Firefox caching that indicate what sites they visited, only the poetry video that they themselves saved. Well, the skeptics among us say that all sounds fine and dandy, but does it actually get rid of all the data that we want it to? Yes. To test this, we put 2 VMs, which were identical up until the point that one of them ran residue-free while the other one idled in the background. On the VM that was running residue-free, we threw the kitchen sink of activity that could generate residue. We installed applications, we used a VPN, we created and saved documents using document editors, we used web browsers to play videos and download documents and intentionally crashed one of them. We used sensitive chat apps to send messages back and forth, and we used file sharing clients to download files from our local network, all trying to generate as much disk activity on common user applications as we possibly could. We then froze both VMs, took forensic copies of both of their file systems and then generated a hash of each file in their file systems and compared the individual files where the hashes differed. All in all, there were only 39 files that had different hashes between the two operating systems, and these were for the most part either timestamps that varied by a few seconds, or unique identifiers that were off, or evidence that residue-free itself had run, which we do not consider to be part of our threat model. None of them contained any sensitive residue about the applications that were run inside residue-free or the data or metadata from them. We also wanted to measure residue-free's performance against the baseline operating system. We found that computationally they were broadly consistent across both graphics operations and CPU operations. The RAM speed was even faster. We weren't able to identify why, but we posited it may be because of caching effects, and network transfer speeds were also broadly consistent. While file operations were significantly slower, less than half as fast in residue-free versus the baseline, we also used some standard user applications, LibreOffice, SFTP, VLC, wget, and Firefox, to measure performance times using pseudo-realistic user behavior, and found that again they were broadly consistent, with a few second delays in more file-intensive operations like converting an OpenOffice document to a PDF using LibreOffice. We also measured the overhead times for residue-free, so the startup and shutdown times, and while they were at their highest, over 17.5 seconds the first time residue-free was launched after a computer turned on. This was also conducted on a computer that has very limited hardware resources, an i3 processor with 2 cores, and launching residue-free on a VM with modest resources or more up-to-date hardware is significantly faster than the overhead times shown here, and most importantly, the shutdown times are very fast, so all residue is removed in less than 2.5 seconds. While our implementation works quite well, it does have its limitations. The first is operating system portability. We definitely benefited from the everything as a file nature of Linux, so a port to Windows, particularly with its system elements that live in memory like the registry, will be difficult. While other ports to Linux distributions should be straightforward with only a few adjustments, we're also working on a Mac OS port where we should be able to keep the logic of our implementation, but will likely have to find an alternative to Docker since Docker focuses on emulating Linux systems. Next, and I have talked about this already, is striking the balance between isolation and access to system resources. Operating systems are famously complicated, so proving that an implementation is able to provide all the resources required by all user applications while removing all sensitive logging potentially associated with those resources is a Herculean lift. In fact, certain applications that require daemonization or integrating with Ubuntu's background services, such as specific VPN clients, snap packages, or specific server applications, they do not work with our current implementation precisely because of this challenge. And different implementations of our proposed architecture can easily end up differing in how they end up on this balance. Finally, our research did not include end-user feedback. While we designed residue-free around usability as a key design parameter, the two limitations I just mentioned are also hindrances to user adoption, not to mention that we did not include a user study as part of our work.
Thank you very much for watching this presentation. The source code for residue-free, as well as the test results that I showed today, and the VM with all of that pre-installed is available on GitHub. Our implementation is designed to be usable and works out of the box on Ubuntu, though it may take some tweaking for other Linux distributions. We're working on a Mac OS port, but any other improvements that you can think of or want to contribute, we welcome with open arms. We've open sourced everything and welcome any tweaks, forks, and contributions. Feel free to send any questions to me via email, or I'm at Logan Arkema on Twitter. With that, thanks again, and enjoy the rest of PETS.